So that's all for the, say, dimensionality reduction techniques. So there are some more, but those are probably the more popular ones. And just keep in mind that the basic idea is that, the time series need to be represented by a smaller amount of coefficients. Yeah, and you can be extremely creative, for example, using different base functions and stuff like that. So usually it's about using some base functions. So now here is this final example for one application-specific feature extraction method. So we call that threshold-based similarity for time series. And the basic idea is that in some applications, only significance events that are defined by certain amplitude values are interesting. Yeah. So and so far the feature extraction typically extracts features modeling certain properties of time intervals, but not of amplitude intervals. Yeah. So for example, here we have some aggregation over time, but maybe we just need some aggregation over the y-axis, so to say, so over the amplitude scale. Yeah. So for example, we are only interested in things that are above some specific amplitude level. Yeah? And we just wanted to know when is the time series above or below that. You know? And where do you need that? Well, there are two killer applications for that. So in environmental science, we use that to analyze critical ozone concentrations. So we wanted to find clusters of regions, clusters of regions. So time series, each region for each region we had time series of those ozone concentrations, and we want to find clusters of time series that exceeds the allowed thresholds in similar time intervals. Yeah. So for example, here this is the critical value. The dangerous ozone concentration is above this one here. Below it's normal, and we are not interested. We are only interested in when is the time series or the region above this threshold, and we wanted to find those regions that have similar intervals of dangerous ozone concentrations. You know? And something completely different, medical diagnosis. So potential, the potential for cardiac infarction, heart disease. So we wanted to find clusters of heart rates by focusing only on the relevant amplitude intervals. And the doctor said, well, if we look at those heart rates here to see if someone has some potential for a heart attack, we just look at we forget about all that stuff above here and all the stuff below here. We just look at this amplitude level here. Everything what is within those two lines here in this red zone here, that is really interesting. Yeah, and that only this is really relevant for evaluating the risk of a heart attack. Yeah, and all the other stuff is just not interesting. And we wanted to know when is the time series, or when is the time series, when are the measurements in this relevant thing here, because we know if it is less or more or less timestamps, then we have more or less. I don't know exactly the correlation. More or less, the higher or the lower is the risk function, the risk level, so to say. Okay, so how we did it? Well, time series have to be transformed. Now we wanted to look at the amplitude level, so we transformed it into a sequence of intervals that store actually, the time slots where it is above the critical threshold. So tau is the critical threshold, like the ozone threshold, or it can be even two thresholds or more thresholds. So in that case, it's just one threshold for the ease of presentation. So we just look at this one here. So we just wanted to record the intervals where the time series is above the given threshold. Yeah, so the threshold is application driven, of course. And what we did is we just recorded the beginning and the end of each of these intervals. Yeah? So a time series is transformed in a sequence of intervals. So this time series here, x, is transformed in this sequence of those 3 intervals here. And each interval is represented by the start point, which is the lower, and the end point, which is the upper. Yeah? So now we can compare time series in terms of interval sequences, and the similarity of time series now should be somehow measured by the similarity of their respective interval sequences. So here is, for example, one specific time series with the corresponding interval sequence, and here is the second one, and here's the third one. You see here that B and Q are much more similar to A, because the interval sequence is much more similar than A. So how to capture that similarity of interval sequences? Well, we can just use a lot of different ideas here. So similarity between sequences of intervals is typically based on a distance on pairs of single intervals. So for a single pair of intervals, the Euclidean distance on the start and the end point is a good choice. So we just take the Euclidean distance of, so if we want to compare two intervals, we just take the Euclidean distance of those pairs of values. Yeah. So if we want to compare, for example, this interval with, I don't know, this interval here, for example, we take the start points and the end points, and just so each interval is a 2-dimensional vector, start and end point, and we just compute the Euclidean distance. That's all actually. Yeah. And then, since we have a sequence of intervals, we just take the sum of the minimum distances between 2 sequences of intervals. Yeah. Which is given by the formula here. So basically, we have to match. So we have 2 sequences of intervals, interval sequences, Sx and Sy, and which represent time series x and time series y, of course, respectively. And for the sum of minimum distance, we need to match each interval from Sx to Sy, which is this one here. And we take the minimum match of from x to y, from the intervals of Sx to Sy, and the other way around. So and we just sum that up. Yeah. So this is actually the sum of the minimum distances between 2 sequences, actually 2 sets of intervals. Yeah. And that is how we did it to define the distance between 2 time series, but in the end. Yeah. Yeah, so just a short summary. We won't do spatial-temporal this week. We will do spatial-temporal data next week. So just to recap, we had the time series this week, talking about different similarity models, hole matching, subsequence matching, and then we talked about similarity measures like Euclidean distance, Minkowski, and then of course on dynamic time warping, which is very often employed. And then we talked about different dimensionality reduction techniques, which are feature extraction techniques, and finally we had this example on a application specific feature extraction technique, which took the amplitude spectrum into account instead of the time spectrum. Yeah, that's it for this week. Hope you stay clean and healthy, and hope to see you or talk to you next week about spatial temporal data. See you there. Stay tuned.